Physical science time. Magnets. Shh. Okay, you need to be quiet. Okay, we're talking about magnets today. So the first thing we talk about is that, like the gravitational force, what's special about the magnetic force? The magnetic force
It attracts things.
it is attractive, but unlike gravity, it's not just attractive. What else can happen with magnets? It can also repel. So the magnetic force is either attractive or repulsive, depending on what side of the magnet. But also it's what? Like gravity, they're both what kind of forces?
Pulling.
No, you just did the same thing.
Not centripetal.
What's special about gravity and magnetism that isn't true about like friction or...
Forces?
Okay, close, better. Yes, non-contact. The magnetic force is non-contact. So does this mean they can't be touching? No. It means that they don't have to be touching. The magnetic force is non-contact. It's part of the four fundamental forces we had. Do you remember what they were? Strong nuclear, electromagnetic, weak nuclear, and gravity. Of those four fundamental forces of the universe, under which of these categories do you think magnetism falls? Electromagnetic. So it's the magnetic part of electromagnetic. That's just to remind you of what we talked about in the past. But yeah, so the magnetic force is part of the electromagnetic force. And so, like gravity, the magnetic force exerts that force in what we call a field, which is, in general, like the gravity field, the magnetic field will attract, but unlike the gravity field, the magnetic field can also repel, right? So a field is a three-dimensional area. No, we shouldn't use that because that means two-dimensional. Who put this smiley face there? A three-dimensional space around a magnet in which this force is exerted, right? So it's a force and it's exerted in a field. What's special about this is that, and it's hard to convey this in your textbook or on the board, but it's three-dimensional. The field around a magnet is not just, like if you look at the picture on page 225, I hope you have the books open. If you look at the picture on page 225, or if when you're watching this at home or if you're watching on the YouTube, you can just look up a picture of a magnetic field. All that will be two-dimensional, and it'll look like this picture here, where we have the magnet with a north and south pole, and it's going to have magnetic field lines that go around it, kind of like that, right? What's inaccurate about this?
It's too deep.
It's two-dimensional. Is there some stuff accurate about it? Well, of course, yeah. We can see the direction of the field lines. We can see where the magnet is operating. So it's not useless. It's just not the whole truth, right? Because the magnetic field is three-dimensional. We call these ends of the magnet. You probably know what we call these. These are both called
Poles.
poles. Poles. There's a north pole and a south pole. What's that remind you of?
Earth. Santa Claus.
Earth. Don't shut up about that man. Don't talk about that man in my presence. No, the north and south pole on planet Earth are because Earth. Can you guess? Earth is actually part of what Earth is. Yeah, Earth has a magnetic field. Earth has a magnetic field. So here's planet Earth. Shh. Here's planet Earth. Well, in this drawing it's flat, but in real life it ain't. Earth has a magnetic field, and it's got a north and south pole just like this magnet. And just like the magnet, the field lines form this kind of shape.
And that's why a compass works.
And this is exactly why a compass works. Thank you, Wade.
And
So
if
when
you
you
get a magnet close to a compass, only a certain side will control a certain side.
right, so the compass is not responding to something inherent about planet Earth. The compass is responding to a magnetic field. So when the compass points north, what pole of the magnet is that probably? We're going to talk about this in a second. It's the south pole, because north and south, just like when we talked about electricity, positive and negative attracted, and positive repelled, and negative repelled. In the magnets is the same way. North attracts south. South repels what? Fill in the blank. South. And if we're talking about north and north, what do?
Oh, they repel.
They repel. So north attracts south, south repels south, and north repels north, right? Opposites, again, just like in electricity, opposites attract. Why might electricity and magnetism be the same in this way?
Because they're
They're-
positive and negative.
Okay, yeah, that's how they're the same, but why might they be the same?
Because they can create electricity.
They're part of what? Yeah, both electricity and magnetism are part of what force? Electromagnetic, you got it. Good job. We talked about this already like 30 seconds ago. So these are the poles of the magnet, and this is how they interact, right? Look with me on page 225 again. We have a picture of the magnetic field lines for a bar magnet on the top of the page, which is what I drew on the board. And then it also shows the magnetic field lines for a horseshoe magnet and for a donut magnet. Do you see how those things look? This is the same kind of stuff you used in your lab yesterday. How do you think we could make a horseshoe magnet?
Well, you bend the magnet.
Bend a bar magnet, right? It's just a bent bar magnet. And then the donut magnet is like a cross section of a flat magnet, right? So if you look at the bar magnet and you cut this little piece out here and pretend it's round, right? It's going to have the same thing, this little round ring with these magnetic field lines all around it. Oh, this is supposed to be three-dimensional. I'm not doing a perfect job, but can you kind of tell what this is?
Just keep on drawing and wrapping a circle around it.
So these are the magnetic field lines of a donut magnet. Something that's kind of cool. Look at page 226. This shows how a compass. I'm looking at the bottom left picture on page 226. It shows if we put a compass somewhere along the magnetic field. So if I put a compass right here, the compass will align with this magnetic field, right? If I put a compass right here, the compass will align with this magnetic field. Do you see that? Like the compass direction will be with the magnetic field. Which end of this compass here is north? Can you tell?
The one that's going to the south.
The one that's going towards the south pole. The north pole of a magnet faces the south pole of the north pole of a compass faces the south pole of the magnet because north attracts south. So when you use a compass, what end of the compass is pointing north? The south pole of the compass is pointing north. It's usually that the north pole, I think, is red. Yeah, that's right. Yes, the north pole is red. Yes.
How does an electromagnetic actually work?
We're going to get to electromagnets in a second. Thank you for bringing that up, though. So, like we said before, the reason that magnets work so you can tell your direction on planet Earth is that they are themselves a magnet. And so when they align with Earth's magnetic field, it points you what direction north is, yes?
Okay, so this might sound dumb.
No,
I'm not
it probably
sure.
doesn't, but let's hear it.
But what is a magnet? Like, how does it get all into one little thing?
Okay, we're going to talk about that right in a second. In fact, that's the next thing in the book.
Okay.
So, start a new section of your notes titled Magnetic Domains. So, there are more elements than this, but the classic, what we call ferromagnetic elements are iron, Fe, cobalt, Co, and nickel, Ni.
Nickel.
Those are what we call the ferromagnetic elements. These are the ones that, because of the way their atoms are, the way the electrons are arranged inside of these atoms, they exhibit, each little atom acts as a tiny magnet. So of these three, each atom, when you have a lump of iron, or a lump of cobalt, or a lump of nickel, each atom acts as a tiny magnet because of the way its electrons are. So for instance, if we have this iron nucleus here, some of the electrons, just because of the way it is, the electrons happen to line themselves up along magnetic field lines, just like a magnet. And there are reasons for this, but they're quantum mechanical reasons, and that's not within the purview of this class. And so suffice it for now that the atoms, every single individual atom in the iron, for instance, is a little magnet. It's a little baby magnet because of the way its electrons are. Okay? You with me so far? Mm-hmm. And since obviously a big lump of iron is made out of iron atoms, what happens is every single, like I said, iron atom behaves that way, but in just a normal chunk of iron like a shovel or other thing, hammer, like a normal just chunk of iron, they're all aligned randomly, right? So what's the net effect? If they're all aligned randomly, what's the net magnetism here? Like on average, what's the magnetism? None. They all effectively cancel each other out. But what happens is that because of so if we have the same thing here, I'm going to draw this a little bit simpler so that I can draw more of them. But if we have this kind of scattered random arrangement of iron atoms, and it's exposed to an existing magnetic field, for instance, planet Earth, or maybe another stronger magnet, all of them line up with that magnetic field. So when they're exposed to a magnetic field, all of these atoms align with the magnetic field, okay? And then this lump of iron is called a magnetic domain, where they all line up in the same way. That's called a magnetic domain. And then an actual object is made of thousands or millions or billions of magnetic domains. And if all the magnetic domains line up, then what does that thing become? A magnet. That's called a permanent magnet. When there's some net magnetism in an object. So when the object itself has a net magnetic field, that object is called a permanent magnet. Does that mean it can't be unmagnetized? That's not what permanent means in this case. In this case, that just means as opposed to, someone had a question earlier about electromagnets, as opposed to an electromagnet, which is not always magnetized. Yes, what was your question, Wade?
So, like you said, not a battery. A magnet can eventually die out. How can you recharge your magnet?
So, if this magnetic domain, over time, something called entropy will cause these to unalign just at random. But also, if it's exposed to another different magnetic field that's in the opposite direction, or sorry, in a perpendicular direction, that'll cause some of them to move in that direction too. And so that'll demagnetize that magnet, right? And so if you want to remagnetize it, you just put it in a strong magnetic field so that they align the same way they're supposed to again, right? And so that's why I am kind of careful when I put away your magnets in your lab that I don't have any that are crosswise like this, because they'll demagnetize each other over time just sitting there, and make sure they're lined up. Not necessarily like North Pole and North Pole, but as long as they're on the same axis. You see what I mean? So that's a permanent magnet. Yes, Payne, do you have a question?
So, if there's a strong enough pull from Earth on a compass to make the compass show you where you're going, how do magnets not point in the direction of the field?
So some of them do. In fact, I have these little rattlesnake egg magnets here, and if I find a place in the floor that's relatively friction-free, we'll do this after I take the video because you can't see on the video anyway, but if you find a place on the floor that's relatively friction-free, these will align themselves with Earth's magnetic field. The reason it doesn't work with like a bar magnet is because since the whole thing's touching, there's so much friction that it can't turn itself, right? The friction force overcomes the magnetic force. But we're going to move on now to talk about something called we just talked about that. Electromagnets. So write down electromagnets next. So permanent magnets are objects which, because of the way they are, exert a magnetic field. Electromagnets exert a magnetic field because of a charge they are given. Electromagnets. So to understand this, we kind of have to apply something called the right-hand rule. So write this down first. Right-hand rule. Right-hand rule. What this means is that if we have a wire, that's a really good drawing of a wire, and remind me, what is electricity? Electricity, by definition, is flow of electrons. So we have an electric flow from this to this, right? So for whatever reason, maybe it's part of a alarm clock, it doesn't matter. But for whatever reason, we have electrons flowing from here to here, okay? So electrons are flowing from here to here. So electrons are flowing this way. Anytime there's a flow of electrons, anytime there's an electric current, we can use our thumb and hand, right hand. It has to be your right hand. So get out your little right hand. Everyone do it. Point it like this. So your thumb has to be pointing the way the electrons are flowing. A magnetic field will be... No, don't do that. The magnetic field will be generated the direction your fingers are going. So it's moving left. The magnetic field lines will go out the bottom, right? They'll come out this way out here, and then they'll wrap around and go back in this way. So look with me on page 231. If you're on the internet, you can like type in electric current, magnetic field. But imagine if you have the electron flow, like in the top image there, it's moving, as I see it, to my left. It wraps around, out on the bottom, and in on the top. Do you see that? So it matches the way your fingers would move on your right hand. This is called the right hand rule. So the magnetic field will be, we use these symbols sometimes in geology. Out as just a dot, and in is a circle with a dot in it. These are the magnetic field lines. Because, obviously, since it's two-dimensional, it's hard for us to represent something coming out of the board, right? If I were to draw this exact same thing, pretend this is 3D, right? We have the magnetic field lines going around this way. This is a terrible drawing. Try to draw it better than me. I'm trying to draw this three-dimensional. Do you see, this is supposed to represent coming out of the board, and they're going around that way.
It's like a spiral.
Yeah, kind of. I don't know. Sure, they're in circles for sure. So the point of this, though, is that anytime an electric current flows through something, a magnetic field is always generated. It's not always a very strong magnetic field, but it's always generated. Anytime a current, write this down. Someone write this down. Anytime a current flows through something, a magnetic field is generated. A great and kind of sad example of this is that Mr. Jones sometimes does something called TIG welding. Are you aware of the existence of TIG welding?
Yes.
Okay, so sometimes he does that. I have, because of the way my computer is arranged over here, my Promethean board has a 25-foot HDMI cord that goes from my computer under my desk, around that wall, and up into the Promethean board. And the way HDMI cords work is a current flows through it, right? So there's, by necessity, a magnetic field generated. The converse of that is that if this wire is exposed to a magnetic field, what can happen with these little electrons in here? Well, it might mess up the flow of electrons, right? And so what happened last year was that Mr. Jones, downstairs right below this, in the shop, was TIG welding, which generates a magnetic field. That's how TIG welding works. There's a magnetic field generated. And because of the length of HDMI cord that I have, it messed up the current. And so every 10 seconds, my screen was shutting off because the HDMI cord current was messed up. I was like, what? Why is this only happening 4th hour? Why is it happening every single day? Why did it just start happening last week, and why did it stop now? Come to find out, it's from the TIG welding, because Dennis Vogel last year was only during 4th hour. And so then what happened was I had Bob get me a more insulated, better HDMI cord, and now it's all better. Woo! So, because, because the current is flowing through this, and so more insulation would mean the magnetic field affects it less. So these electromagnets exist only while the current is flowing. So if I disconnect this battery, what happens to the electric field? Gone. When might this be useful? I can think of a lot of reasons. There's a lot of times in my life when an electromagnet would have been useful. When would you ever want there to be a magnetic field sometimes and not others? When would you want a magnet you could turn off?
Like picking up a car in a junkyard.
There you go. Okay, that's exactly one. They use electromagnets, very, very strong electromagnets, to pick up cars in a junkyard, right? You don't want to use a permanent magnet because that sticks to the car and then it's just forever on the magnet. So they use an electromagnet, pick up the car, bring it to where it needs to go, turn it off, and it falls off, right?
Some boats have them to pick up.
Oh yeah. If you're running like a salvage boat or something, you need to pick up something off the ocean floor. I use one, or I would like to use one. I don't own one, but I know that people sometimes do use them for roofing. They have a little push electromagnet. Flip on the switch, the magnet turns on, go around, pick up all the nails, put it over the dumpster, turn off the switch, and all the nails fall into the dumpster, right? Because gravity overcomes it. So it is a useful thing. We're going to talk about 2 more things real quick here before we're done, and then you're going to read through this on your own. But we're going to talk about motors and generators. And we're going to talk about them together because they're kind of I wouldn't say opposites, but they're kind of 2 sides to one coin. Motors and generators. So, yes, Peyton.
Are you gonna show them the copper?
Yeah, not right this second. Let's briefly define them first. A motor, as far as energy goes, a motor is something that changes electric energy to what? Can you guess? Kinetic. And a generator, what do you guess that does?
Into
Changes.
Whoops.
changes kinetic energy into electrical energy.
Yep, changes kinetic to electric. And both of these work on the principle of magnetism. They both work on the principle of electromagnetism, to be specific. So, let's talk about motors first. Let's talk about generators first. Let's imagine we have, to me, a simple kind of generator is a wind generator. So here's the wind mill, right? And it has this thing on the back of it. You've ever seen a windmill way up high in the sky? It looks quite a bit like this. This is a very good drawing of a windmill. So this windmill is attached in here to a generator. And so what happens is as the wind spins the windmill, right, it causes this bar to spin too, and the bar has a magnet attached to it. So this little thing here is a magnet. And as the magnet spins, it's inside this coil of copper wire. As the magnet spins, what must that do in the copper wire?
Charge.
It produces we don't call it a current. A charge is what?
Electrical charge.
It produces an electrical current, right? So it produces an electrical current, and that current flows out the windmill and into your little house, right? So you can run your microwave oven or your Xbox, right? So all that's happening is that this movement of the wind, that's happening is the movement of the wind is causing this magnet to spin, and as the magnet spins inside that copper wire, it generates an electric current, and that current can be used to power electrical objects, right? It's the exact opposite in a motor. In a motor, we use electric charge. So I'm going to use this little example here. Here's a wheel. This is a wheel. This is a really good drawing of a wheel too. I should be an artist. And inside of here, so this is connected to, we'll say, a battery. This is a battery. This is not the correct symbol for battery, but there's an electric battery attached to this copper wire, and as power is supplied to the wire, it causes that magnet inside of there to spin. And when the magnet spins, it causes this thing to spin, right? So they're just opposites. This one uses electric energy to make something spin, and this one takes something spinning to cause electric current to be produced, right? So what are some other ways that we can use this? It's not just wind energy. What else could we do?
Electric.
Yeah, we could use hydroelectric, right? If we had water flowing over this instead, it would be hydroelectric. What else?
Pulleys, when a car's running, the bolts move over an alternator and magnet.
Yeah, okay, that's true too. But we're talking about other ways that electricity can be generated. You may not know this, but this type of electric generation is the same thing that happens in a coal power plant or a nuclear power plant. It doesn't make any difference. In those things, though, there's some, we'll say coal here, right? There's a vat of water here with a little outlet, and inside the steam outlet, there's basically this exact apparatus here. So as the coal starts on fire and gets the water hot, the water turns to steam, and then the steam causes this turbine to turn, and the same exact thing happens. As far as I know, except for solar power, which works on a different principle, every kind of power that we commonly use, nuclear, wind, hydroelectric, fossil fuel, geothermal, all of them use this technology, which is a turbine. We call this thing a turbine. The thing that spins, which causes the magnet to spin, which causes electricity to be produced, it's called a turbine. All of those power production species, I don't know, things, entities, are affected by a turbine. Your book goes on to talk about the difference between direct current and alternating current. Basically, it's fairly simple. The alternating current happens when we produce electricity in this way. Because of the magnet spinning in there, it alternates between electricity flowing this way and electricity flowing this way. It just kind of oscillates back and forth. And that electric differential still allows your Xbox or your microwave or your phone charger to have power because it's still moving electrons. It's just that they move back and forth instead of in a straight line. That's called alternating current, AC. This, where the electrons are only flowing in one direction, like in a battery, that's called direct current. And we'll talk a little bit more about that off the video, but effectively that's it. Alternating current is just when the electrons are kind of wiggling back and forth, and direct current is when they're actually moving from one place to another.
So DC battery.
Yeah, batteries, in general, batteries are DC and wall outlets are AC. In general. There are some exceptions. You have questions about, so we talked about magnets and magnetic fields in general. We talked about permanent magnets and magnetic domains, and we talked about electromagnets, which includes motors and generators. Do you have questions? I want to hear, I mean, you asked your questions throughout, but do you have other questions? Do you have an understanding of what you'll be responsible for knowing, kind of? I mean, this is a pretty broad overview, but we touched on all the big stuff in here. You don't have any questions?